Space, the final frontier. These are the voyages of the Starship Enterprise. Its 5-year mission to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before.
Welcome to Mono Lake, California, where there has been a life-altering discovery. This discovery will not only change the perspective of how life is viewed, but more importantly, how life is evaluated. As scientists look to the stars for extraterrestrial life, perhaps the approach they have been using has been the wrong one. When it comes to life here on Earth, there are 6 fundamental elements commonly associated with the existence of terrestrial life here on this planet. They are referred to as CHONSP, carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. Without these, life cannot exist, or so it has been assumed up until now. Before this gets started, there must be a brief description or interpretation to what the definition of life is. Life must have metabolism, a reaction to foreign stimuli, the ability to reproduce, and most importantly, life must want to live. Following these basic fundamentals will help us to define the following. If evolution has taught us anything, it is these abilities and modes of adjustments that allows for life to continue on. One of the unique qualities is Mono Lake's diversity of life. However, the more fascinating part is the high concentration of natural arsenic. Arsenic is very dangerous and fatal to biological life, and is also very unstable. In small doses, it can cause growth defects and sterilization, along with visible tissue scarring. Large quantities are nothing less than fatal. But it is here, in Mono Lake, California, where astrobiologist Felisa Wolfe-Simon leads a team of researchers to seek out the unthinkable and found the inevitable, endogenous alien life. And after a year of research and scientific methodology, their findings have put the biomolecular world upside down and inside out. Here, Felisa is taking samples of this mysterious bacteria from the lake's floor for further study. It is no surprise that organisms can survive in arsenic-saturated areas. However, the organism known as GFAJ-1 not only lives in this harsh environment, but it can also substitute its DNA of phosphorus with arsenic. What this is saying is that the way that life is looked at and how scientists span the universe for other life, it is feasible that the spectrum of life is greater than previously presumed.
All life that we know of requires carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And it uses those 6 elements in some of the critical pieces I think we're all familiar with, including DNA and RNA, or the information technology of the cell, the proteins, which are the molecular machines, and the lipids, which separates you from everything else. And so we've discovered an organism that can substitute one element for another in these major biomolecules. We've cracked open the door to what's possible for life elsewhere in the universe. And that's profound. And to understand how life is formed and where life is going. This microbe substitutes arsenic for phosphorus in its basic biomolecules. And what else might we find? What else might we want to look for? So here we're seeing the beautiful, elegant structure of the double helix of DNA. And what I want to highlight is the phosphate backbone, we say, and that's the light orange balls. And it stitches together as we see the edges of DNA. It holds together the DNA, the backbone. And so what we think is happening, what all the evidence we've collected suggests, is that instead of these, we'll see these orange, light orange balls disappear. And represented by green balls, we see that arsenic would be substituting for phosphorus in the backbone of DNA. And you can see how critical this component of the DNA. Arsenic lies just below phosphorus on the periodic table, and so they actually have the physical size of arsenic and phosphorus are very similar. We call it the atomic radii, but it's the physical size of the atom, as far as we can tell, is very, very similar.
The skeptics.
Parsimonious way to interpret this. Arsenic was absolutely associated with the DNA fraction, purified on a gel. To address what Steve's saying, how it survived all the manipulation, if you're aware of how we do DNA extraction, unknown. It migrates at a different level. I'll be a bit technical for a second. Migrates at a different rate. I think it's supercoiled. I've done things like cesium chloride gradients. Again, a little bit technical. It's weird. And I'll be honest, I've been asked a question like, well, what did you think? Were you Eureka? No, I'm a biochemist. I said, this isn't right. Something's wrong. I must have made a mistake. And you'll see there's a laundry list of fantastic co-authors. And I got a reputation at meetings. Somebody would give a talk, whoa, I think that's a type of mass spectrometry. You could do this. And so they see me coming. They wouldn't know who I was, but they knew that I was going to ask them to measure something for me. And often I asked them to do it blindly. And they often said, and if I were there, we would stare at the data, and they would sit back, very experienced scientists. What am I looking at? No, what do you think it looks like? No, Felisa, what's in the sample? No, what do you think it looks like? It's often 2 a.m., you know. So the answer, from my viewpoint, in how much arsenic is substituting, I think right now we don't know. If you look at the data that we're presenting in the paper, it varies. And again, to be technical for one moment, we've measured these cells in stationary, so it's old age for the cell. So they've reached a point, you grow, stop. And so the idea there is normally we run experiments a little differently. So if you look on our supplementary evidence, we've showed we're very transparent. There is absolutely some phosphorus left in these cells. But what's unambiguous about those numbers is it is not enough to support the growth that we observe. Right? 2.8 femtograms. It's just not enough. So to support that growth, we can estimate what we call this in science the back of the envelope calculation. We can squint and see that pattern in nature that our data are telling us. We can estimate how much total phosphorus you need at a very low, how many ribosomes, how much you need in the genome, how much you need on your proteins to turn them on and off. It's called protein phosphorylation if we have the analogous problem with arsenic. How much you might need in the lipid. It's just too little. It's just flat out too little. Do we have a crystal structure yet? No. I have collaborators working on that. Do we know the genome yet? No, but we're going to work on that. And the point was, it could be maybe it's just A's and T's. Maybe it's just G's and C's. Maybe it's 1 out of every 10 or 2 out of every 4. Great question. So what we're not suggesting, in my paper, I tried to write it in a very clear manner. What I'm not suggesting is that if the entire microbe is made of arsenic. Absolutely not. I'm very, very transparent. My co-authors, we spent a lot of time being very careful. We're not really speculating. We wanted to present the phenomena to the community and to the public. Say, oh my gosh, this is amazing.
As one skeptic put it, I wonder if this is a separate instantation of life on Earth, or seen as early Earth had lots of volcanic activity and lots of arsenic. If early life formed based on arsenic and then later replaced it with a more stable phosphorus, it's said that the arsenic chains form more easily and avoid some complex step that phosphorus chains require. So we either have two abiogenesis events or are closer to knowing the first abigenesis events.